everybody and welcome to the next edition of NPTEL online certification course on microelectronics devices to circuits. Today we will look into the design of feedback amplifiers against all its configuration, various configurations of the feedback amplifier. In our previous module we had looked into the fact that what is a negative feedback, how does a negative feedback work, what are the criteria for the multiplication of A and beta, which is basically the feed forward amplifier, and beta, which is basically my feedback ratio, so that I am able to achieve a value of negative feedback. And we saw that if A beta is greater than 1, we automatically get a lower gain. So the advantage of a negative feedback, we get a higher bandwidth, we get a less distortion, nonlinear distortion. We also have a much more stabilized gain in the output side, and these are the few advantages which we saw. We also saw in our previous turn that when you do have those configurations of series shunt or shunt series network, we generally are able to modify our input impedance and output impedance of an amplifier. And the advantage of such therefore negative feedback is that I am able to therefore have my output impedance change with various configurations. Now, since the amplifier output drives a extensive load and the load will be a varying load, I can therefore match the output impedance of the amplifier with the load itself for the maximum power to be transferred. And I can use, how can I do that? By applying various configurations of negative feedback. So, we have done 4: series shunt, series, shunt series and shunt, right, and we have seen how the input impedance and output impedance change. Today the topic of today's topic is basically my feedback voltage amplifier. So, we will look at the ideal case of a series shunt amplifier, right, and then we will look into a practical case of ideal of the series shunt. Then we will look into an ideal and real case of series feedback network, right. So, we look into series feedback. We will also look into shunt case. So, for all the cases we look into ideal case. Ideal case is when you do not have any loading, right, which means that your feedback network does not load your amplifier and your amplifier does not load your feedback network, and they are two independent entities we have assumed. In the second case, when you take a practical amplifier, we assume that there is a loading effect coming into picture. So, we have all the 4 amplifier: voltage amplifier, current amplifier, transconductance amplifier and transresistance amplifier for ideal case as well as for the real cases. So, let us look at the feedback voltage amplifier. This is basically a series shunt, and let me show to you the series shunt feedback network here. As you can see here, this part, which is basically my dotted part here, is basically the amplifier. So, this is the A circuit. When I say it is basically your amplifier circuit, and the blue one is basically my beta circuit, which is basically my feedback circuit. So, this is my feedback circuit, right, and this is my amplifier circuit, right. So, amplifier is a feed forward and this is basically my feedback. Now, this is a series shunt, which means that I will be extracting a voltage from the output and feeding back in the form of current in the input side. So, the input side you have an input current here, right, and you have output voltage which is V0, and this V0 therefore appears here, right, and a part of V0 appears as a voltage source in the output of the feedback network. So, say your beta is equals to 0.1, it primarily means that 0.1 times V0 will be your output voltage here of this network, right, of this network. So, your Vf will be equals to 0.1 times V0, and as a result this is how we will generate the feedback ratio. Vi is basically, so Vs is the source voltage which you see, out of which a particular voltage Vi appears here depending on the value of Ri, which is the input resistance of the amplifier. Now, typically if it is voltage gain, A equals to therefore VO by Vi, right, and therefore VO will be equals to A times Vi, and that is what is written here, it is A times Vi which you see. You will also have an output impedance of the voltage source here, and therefore that terminates under the output side, right, and depending on the value of beta and A0 we will see how it works out. So, we can therefore converge it into this factor or into this form, that I have a source voltage which terminates onto RIF, which is basically my input resistance with feedback. I have a output resistance with feedback ROF, F suffix means feedback, and my voltage gain is given as AF times Vs, right, and my output voltage will be given by V0 here, it is given by V0 here. So, with this knowledge or with this basic idea, let me show to you how I am calculating the ROF and RIF. Now, we know that AF will be equals to V0 by Vs, right. AF is means the amplifier gain with feedback, right. Amplifier gain with feedback primarily basically it effectively means that I am trying to look at this voltage divided by this voltage, right, and that is what we are trying to find out when we say AF. And if you solve it, I get A upon 1 plus A beta, which we have already done earlier also, and we saw that AF is therefore always less than A, right, and therefore there is drop in the gain. Now, you see Vi will be equals to Vs upon 1 plus A beta. From where did you get this Vi upon Vs upon 1 plus A beta is basically that so what Vi is the input voltage. Where is the input voltage actually referring to? Input voltage is basically this voltage which you see, right. So, I am looking at Vi by Vs. So, this by this will nothing but be a voltage divided network, and I get Vs upon 1 plus A beta. Therefore, current, if you want to find an input current, you have to divide this whole quantity by Ri, that is what I am doing here. Now, so therefore, if you look very carefully, if you transfer this to on the left hand side, I get Vs by II is basically equals to 1 plus A beta times Ri. This is nothing but RIF. So, RIF equals to 1 plus A beta into Ri, right, which means that my input impedance rises with feedback. Look at the output impedance. How do you find out output impedance? Is very simple. You try to short the input and give a feedback voltage here, and then apply a source voltage Vx at the output side and try to find out the current. Vx by Ix will be equals to Ro, right, and with respect to feedback I will get the value of Ro. So, I write Vi equals to minus beta times Vx. Why there is a negative sign? Because you are doing a negative feedback. So, a part of Vx appears as Vi input side, I get minus beta times Vx. So, if I want to find out Ix, which is the current flowing through this arm, this current I want to find out, then this will be nothing but Vx is the voltage divided by Ro, which is this one, right, into 1 plus A beta, right, into 1 plus A beta. And therefore, if you want to find out, you will get, so from this equation what I can get is basically Vx by Ix will be equals to Vx by Ix will be equals to Ro upon 1 plus A beta, and this is nothing but ROF. So, I get ROF is equals to Ro upon 1 plus A beta, which means the output impedance with feedback falls down by a factor of 1 plus A beta, but my input impedance rises by a factor of 1 plus A beta. So, my input impedance rises and the output impedance falls down. You can see it physically also. Why? Because if you look very carefully, then you will see that that this is basically a series addition here, and therefore your impedance levels will go high. This is a shunt or a parallel addition here, and therefore your impedances will go low, right. That takes care of approximately all the understanding here. Now we do the same thing for all the 4 networks and see how it works out. This is basically a series shunt, the previous case, but let us look at a practical case in reality, which means that you do have a loading here, I have a load here, and I have RIF is the input resistance which you see, Rn is basically my input resistance without feedback, and RIF is the input resistance with feedback. Now, Rs is basically the voltage source here. What we try to do is that we try to convert into a 2-port network, right, which is basically my H parameter analysis which we do, H parameter analysis. H parameter is also referred to as a hybrid parameters, and it correlates voltages and currents together, right. So, what we do is basically that we design the feedback network properly, and we say that there is a load resistance which affects your basic amplifier. I have a source resistance here. Out of the voltage available at this point, which is V0, I say that I can model is H21 I1, H21 I1, and this will be basically so H21 is basically a current amplifier, and into I1 if you do, I will get the overall current flowing, and therefore, this is represented by a current source. And similarly H12 into V2. So, there are two terms here, H11 and H22. H11 is basically nothing but a series resistance, H22 is basically 1 over resistance term, and therefore, you see it is coming parallel to the current source, right, as and you can appreciate as well, because current sources, ideal current sources will automatically have a very large output impedance, and that is taken care of by H22 in a reality. H12 V2 is nothing but the voltage source which you see here. So, this is basically a voltage source here, a current I1 is flowing through this arm and a current I2 will be flowing through this arm, this is I2 in a 2 port network, this is H11, H22 which you see. With this knowledge, we can safely write down that H21 is nothing but V1 by V2 with I1 equals to 0. What is H12 therefore? H12 is nothing but, if you look very carefully, H12 I am referring to as V1 by V2, V1 by V2 with I1 equals to 0, or I1 is open, I1 equals to 0. I1 0 primarily means that you are opening the input side, right, and that is pretty important, that you are opening the input side. So, your input side is open, in this case this is the input side and this is considered to be open. In that case I get H12 equals to the ratio of the two voltages V1 by V2, and therefore, you write here V0 which is the voltage source, and then H12 V0, because this is the input voltage, this input voltage multiplied by H12 will give you the value of the output voltage, and that is also referred to as beta and also referred to as H12, right, and I get, and therefore, I get R. So, what I do is I shift this H22 which was initially here back to this place. So, now you have got RL parallel to H22 as the overall loading on the output side, right. Similarly, the H11 which was initially placed here comes in series to RS, right, and you can place it in series to RS, right, and that is what we are trying to do in this case. So, if you therefore fall back and let us see how it works out, we see that the amplifier circuit will be modeled as an RS and R11 in series to basic amplifier and R22 and RL parallel to the basic amplifier in terms of loading, right. So, as I decided to you, that gain will be defined as V0 by Vi, which is where V0 is the output voltage and Vi is the input voltage, and V0 by Vi will give you the amplifier gain, which is basically A here, right. How do you obtain the value of beta, which is the feed? So, beta is referred to as Vf by V0 where when I1 equals to 0, and beta is obtained from this network. That what you try to do is you open circuit the input side. When you open circuit it, I1 equals to 0, and then what you do, you give voltage V0 and then try to find the voltage at these 2 points. Vf by V0 gives you the value of the feedback factor beta, right, and that is what an interesting part of this whole network part is there. We come to now the feedback transconductance amplifier, and this is basically a series case. Series as you can see that I am adding the voltage or current here in series and I am extracting current here in series as well, right. So, I have a current source here which is giving me I0 or the output volt current, this flows through this path, right, and you get this into consideration, this current flows back into the system, and therefore, I can replace it by giving Ri here, Vi here as in the previous case, and then I say that A times Vi is sort of the voltage source which you see here, and parallel to that, but this will be basically a current source here. So, Ai is basically I by V which you say, right, I by V which you say multiplied by V gives you current, and therefore, that is the current source here A into Vi. A is basically my del ID del Vg, which is basically transconductance, and that is the reason A will be referred to as transconductance. Many people write this also as Gm times V1 here also, and they get a reason for that, right, and I have a current source I0 and then beta times I0 is the voltage source which you see here, and that gives me a value of the output voltage which is the feedback voltage at this particular point. You also therefore can come back to this equation or this diagram and show that therefore, that I have therefore my input resistance feedback resistance here, I have my output with feedback ROF here, and then AF times Vs is nothing but the current source which appears to me by virtue of my feedback current or the feedback value. So, this is my source voltage and this is my output voltage in practical sense. Now, the same thing we bring it back here and show to you what is the implication here, and in both the cases you will see that RIF, I am not doing the whole derivations given in all the standard books. I get RIF basically equals to Ri into 1 plus A beta, which means that the input impedance of the transistor, in this case an amplifier, depends on the factor of Ri, which is basically without feedback the resistance available to me in the input side, multiplied by 1 plus A beta. So, what happens is that RIF is obviously greater than Ri by a factor of 1 plus A beta. Since A beta is relatively larger as compared to 1, I can safely say that RIF is equals to Ri into A beta. Now, ROF, if you want to find out, which is basically the output impedance, then I can say simply it is equals to Vx by Ix. Where is Vx? Vx is this voltage which you see in front of you, and this is the voltage which is appearing here. Upon Ix is the total current which is flowing through the device, and that is your ROF. So, if I get Vi equals to minus Vf, because it is a negative feedback, Vi equals to minus Vf, and therefore I can replace Vf by beta times I0 by my previous definition, which can be also referred to as minus beta times Ix. So, I0 is the output resistance, output current which you see here, which is exactly the same as value of Ix here. So, now what I try to do is I get Vx equals to Ix minus AVi times R0, because AVi will give you the current here multiplied by R0, and then if you solve it I get A times, so Vi will be broken up into A times beta times Ix into R0, and therefore ROF is equals to 1 plus A beta times R0. So, you see now, as I was predicting earlier also, that the input resistance with feedback and the output resistance with feedback both increases by a factor of 1 plus A beta, right, and that is quite a heavy increase here, where A is the feed forward open loop gain of the amplifier and beta is the feedback fraction. Beta in this case again is referred to as Z12 and is given as V1 by I2, and its dimensions in the order of ohm with I1 equals to 0 primarily means that your input is basically open. So, you see input has been kept open here, right, and trying to find out the current available at. So, AF will be defined as A upon 1 plus A beta as per my previous definition, as we have already discussed this point in details. Now, let me come to the practical case of a series amplifier, and you see here that I have broken down the feedback network into Z11. So, it is basically a Z parameter which is available to me. So, Z11 and Z22 are basically the resistance, input resistance and output resistance offered to the device, and I get Z21 I1 and Z12 times I2. So, you see your feedback network is changing. So, if you look back your previous discussion here or maybe this previous case, that if you look here and then you try to find out, in this case you see we were talking in terms of, if you look very carefully here, what we were talking was that your this was your H parameter network, right, H parameter because you are dealing with both current and voltages here, whereas now when you are dealing with both sides current or both side voltages or both side current maybe, then you need to deal with the fact that you should have a current amplifier with you, and that is what the reason the current amplifier is with us, and therefore Z11 and Z12 are nothing but the voltage sources or the impedances seen to it. Z12 I2 is the current flowing through the device, and Z21 I1 is the current input into the device in the feedback network, right, and I get I0 as the total current flowing through the device. Now, we look at the basic amplifier and then we just take Z11 from its initial position and make it in series to the RSS value, and Z22 in parallel position we parallel to RL, and then I get Z12 I0 as the input current source here, right. So, I have a current source here which is shorted, and I get Z12 I0 as the output current source which is fed back into the basic amplifier, which converts the current into a voltage, corresponding voltage, and the output value is created, right. As I discussed with you that in a typical example which we follow, we see that these two are in input side and these two are in output side, right, and we say that R22 and RL, which is the load, external load, are related to each other just like RS and R11 is related to each other. We also define gain to be equals to I0 by Vi, which is basically output current by input voltage. Now, beta is obtained from the fact that if I1 equals to 0, I get beta equals to Vf by I0 with I1 equals to 0. This is how you calculate the value of beta, right. So, it is feedback voltage by input current, that is how you define your beta value in all respects as far as this feedback is concerned. Now, let me come to the shunt ideal case. In the shunt it will be, if you remember, both sides parallel, and therefore, you see this is Ri, which is the input resistance which you see, and then you will have output resistance R0, and this A into Ai or A into Ii is nothing but a current source, what do you say, a current source which is basically your modified current source as compared to an ordinary one, and this is Ri which you see, and therefore, this is Ro is the output impedance which you see here. They are parallel with respect to each other, because both sides you have got shunt and shunt, right, and therefore, I can write down AF equals to A upon 1 plus A beta, right. And if you go back to your ideal shunt cases, I get RIF, I get ROF, and you have got AFIS, which is basically a controlled current source, which gives me a value of output current for various values of AF chosen, right. Now, therefore, I get II input current to be equals to IS minus IF because of negative feedback. We already know IF to be equals to beta times V naught, and since V naught is nothing but A times II, I can safely write down IF to be equals to beta times A times II, right. So, I get II equals to therefore IS upon 1 plus A beta, and therefore, I can safely write down input impedance or input source is basically XS, input current source is Xi, and therefore, I can safely write down RIF equals to Vi upon 1 plus A beta times Ai, and RIF equals to R by 1 plus A beta, and ROF is equals to RO upon 1 plus A beta, which primarily means that whenever you are trying to find out an impedance, 1 plus A beta term will surely come in the denominator, and that will make my impedance level go down with feedback. We can change the value of A and beta and get new values of RIF and ROF, right. So, this is what we have learned in this module. In general, we have learned this basic concept here. Now, let me come to the case of feedback resistances here, feedback shunt resistances and shunt series resistances. So, I get a shunt series basically means that I will take a parallel output here, and I will do a series input at this particular point, right. And therefore, you see I have got Ri here, and then A into II. A is basically my current gain, right, current gain, and it is given by Ai, and this will be current gain which is visible to me. So, the total current will be nothing but I0 upon II multiplied by II gets cancelled out, I get this equals to I0, right. So, when you short and therefore, resistance is low, your current becomes large, and as a result we also get a large current at the output side, right, which is beyond our control to an extent, because all the current is now being routed through the upper arm. So, what we do is that we put an extra resistance here, which is basically in parallel, and then try to route this current through this arm onto a device which is basically takes care of the increased value of voltages, and therefore, increases the current flow through it. So, as I discussed with you, since this is a shunt series feedback, I will get my input impedance lowered by Ri equals to 1 plus A beta. However, my output impedance will also get lowered by 1 plus A beta. So, both the input impedance and output impedance falls down by a factor of 1 plus A beta. Let us look at the feedback current amplifier. It is basically a shunt series application. So, I have got a shunt here, right, and I have got the series application here. So, I get RS is parallel to R11, and I get R12 here in this place multiplied by RL, right, and this is my output impedance. I have just shorted it because I do not want any output impedance to confuse at this point of time, where R11 is defined from this network, and R12 is obtained from this feedback network, right, and from these two feedback networks they can actually find out the value of the resistances or the impedances which is there in the system. Beta can be obtained from this feedback network in a general manner. Okay. So, to recapitulate, therefore, let me show to you what are the recapitulation points, that when you have a series topology or a series shunt topology, your feedback amplifier is generally a voltage. Whenever you have a shunt series, it is basically your current. Whenever you have series transconductance, and whenever you have got a shunt, you do have one of the scholars who will take care of your problem, right, and that is basically the transresistance transresistance Shunt-Shunt. So, in transresistance Shunt-Shunt both the resistance fall down, right. In case of series both the resistance go up, input output, and in case of Shunt-Series input falls down, output increases, and in case of series this rises and this falls off. So, depending upon whether you are in series or shunt, the resistance offered will be always increasing or decreasing depending upon the virtual position of the human being, right. And that is what we learned from this whole idea, that wherever you are placed in the circuitry, depending on whether that is series or shunt, you will be able to predict whether from first principles whether you get a low resistance path there or a high resistance path in that case. Okay. So, I have got 4 types of networks available with me: series shunt, Shunt-Series, series and series shunt. Whenever you get a series, you get an increase in the impedance; shunt, you get a loss in the impedance. If you want to generalize the whole term, I get Z is the impedance which you see with feedback is equals to Z, just Z you can write down, ZO, which is basically your output impedance, into 1 upon 1 plus A beta when you want to show an decrease, and this is how when you want to show an increase, right. We have already discussed this point earlier. We also can show you that overall if you want to make it as a function of frequency, then Z of f is equals to ZO of S upon 1 plus A of S into beta of S, right. And that is quite critical, that if, because we have till now believed that the amplifier is basically frequency independent, and basically we are talking about the mid frequency gain in which your AS will be independent of the frequency, right. And that is the reason this is a safe way to play out the values of ZOF and ZIF, right. And you can actually get those values in a detailed manner here. And if you remember, what we did therefore was applying Kirchhoff's law, first order Kirchhoff's law, to get the values of the impedances here, right. With these words, let me thank you for your patient hearing, and we will take up the next module of stability and poles and zeros applied to amplifier our next module. Thank you very much.